Hi, Colton. Welcome to class. We are going to move on from significant digits, and we're going to start with motion, and I'm going to let, is this the right size? It is, yeah, yes, it is right. Let a young lady from India explain to you a crash course that she will talk very quickly. She's going to cover most of the things that we're going to do in the first chapter. That's not you. It could be you, Colton. You could go ahead and eat if you were hungry, but we can't. Actually, I can anyway. I just have more water. It's one of those doctor's appointments you get to fast, but you have to be blood draw, so you have to be completely hydrated. Well, that's part of it. Yeah. So it's a. I don't mind that. I donate blood, so this will just be just a little tube. That's nothing. But you have to fast. That's not as easy. Yeah.
I'll fast with you.
No, this is not for any religious reason or anything. This is just doctor says you can't eat. So she's going to go through everything we're going to do very quickly, and then we will go through slower. And remember the formulas. You will get a formula list. Well, you won't get it. You'll make a formula list. So you don't have to take notes on this. The notes that you'll eventually get will be the formulas that are on there. And then you will get to use them. And they will be, for the first part here, pretty simple. One of them is when we get to it, is a quadratic. One that isn't too bad. There's a certain time where we eventually will get to where you have to use it as a quadratic function and actually use the quadratic formula, but you already have that written down on your formula list, so you're good. Most of the time it will be much simpler than that. It just happens to have a square in it. But so I will let her explain it to you first, and she will give you a lesson in traffic safety and how to, you can turn the light. I think this will pick it up.
No more purple sheet.
No. You can still spend quality time with it, though, if you'd like to.
Hi, I'm Dr. Shanice O'Mara, and I hear you want to learn physics.
Yeah.
I have to say, good choice. Physics is the science of how the world, really the whole universe, works. And I don't know if you've noticed, but the world I live in, things tend to move around a lot. So that's what we're going to study first, the science of motion. And it turns out to be incredibly useful for figuring out things like where you are, where you've been, or how you're moving through the world. Why is that worth knowing? Well, for one thing, the police use physics to decide exactly how fast you're moving through the world, and if that motion happens to break the law. So if you're going to understand how and why you got that ticket they gave you, and maybe even know enough to dispute it, you have to know the science of motion too. And in order to do that, you'll need to understand a few essential conditions that describe your physical place in the universe. Conditions like time, position, velocity, and acceleration. So to talk about all of these things at the same time, you'll need a set of equations that links all of them together. These are called the kinematic equations. So for the next few minutes, let's talk about how you can figure out your place in the world, literally, which just might help you beat that speeding ticket. Let's say you're driving on a straight stretch of highway, say someplace nice and flat, on the wide open spaces of the northern plains of the United States, say North Dakota. You come across a red light, and even though there are no cars in sight, you stop, because you're a good driver who obeys traffic laws. Then the light turns green, so you hit the gas, and exactly 7 seconds later, you hear the sirens and see the flashing lights of a police car. You're promptly served with a ticket for speeding in a 100-kilometer-an-hour zone. But wait, were you really going that fast? Did you actually break the law? You can't really tell because the speedometer in your car is broken. So you need to find another way to figure out how fast you are going and decide if you want to take this up with Johnny Law in court. That's where physics comes in. The physics of moving in a straight line. Let's start by talking about how your car was moving. Driving along a straight highway is an example of one-dimensional motion because the car can only move back and forth along that line. That's the difference from something that's free to move in all three dimensions, like a boomerang flying through the air. And instead of describing that motion just in terms of speed or direction like a police officer or other non-physicists might do, we physicists describe it with maths that measures the four main conditions of the car's movement. It's time, position, velocity, and acceleration. Time simply tells you how long you were driving for. Position is also important. It lets you know where you are and where you were. It can even be negative. For one-dimensional motion, there are only two directions you can move in. In this case, forward or backward, east or west. So if the change in position, known as displacement, is positive, you'll know you've moved in one of those directions. If it's negative, you're travelling the other way. But which direction is positive and which is negative? That's totally arbitrary. You could decide that east should be positive and west negative, or the other way around. But the answers you get will mean the same thing. You just have to make sure to keep track of which direction is positive and keep that in mind when you're talking about velocity and acceleration too. Velocity is the way your position changes over time, and it's also a pretty big deal. It's kind of like speed, but just like with displacement, it also tells you which direction you're moving in based on whether it's positive or negative. Now, what about when your velocity changes? That's the fourth quality of movement you'll want to pay attention to, acceleration. If you've ever been in a car when someone slammed on the gas, that feeling of being pressed back against your seat is acceleration. Your velocity is changing. So how do we plot out all of these different conditions that describe the movement of you and your vehicle through the plains of North Dakota? A non-physicist might visualize this movement on something like a map, but for us, graphs are the most useful way to show how all this change in position is happening. Graphs are generally presented as position versus time, with position on the vertical axis and time on the horizontal axis. We'll label your position as X and time as T. Now let's imagine three different scenarios for how you drove through this small town and graph each one. First, let's say that after you went through the red light, you just stayed in one spot, say at 4 meters from the light, for 3 seconds. From that moment, the graph of your position would just be a flat line at X equals 4 meters, like this. Now what if you didn't stop, but instead were coasting at 1 meter per second? Then the line would be diagonal to show how your position was changing, like this. And the third time, let's say you were standing still at first at the 4 meter mark, but then you hit the gas. And you moved in such a way that after 1 second you went 1 meter in the positive direction, and after 2 seconds you went 4 meters, and after 3 seconds you've gone 9 meters. In that case, you end up with a graph that's all curvy like this. But there's more going on in these scenarios than just your position and time. You also have to be able to graph your velocity and acceleration. So to graph your velocity, you'd put your velocity on the vertical axis and time on the horizontal axis. And you'll note, since velocity is measured as the change in position over time, it's measured in meters per second. The graph for acceleration is quite similar. Acceleration, A, goes on the vertical and time goes on the horizontal. And since acceleration is measured as the change in meters per second, its units are meters per second, otherwise known as meters per second squared. So time, position, velocity, and acceleration all relate to each other. Velocity is the change in position over time, and acceleration is the change in velocity over time. And often, your velocity will be different from moment to moment, like the third time you drove down the highway when you hit the gas. But let's say you wanted to know your average velocity for a certain period, say for those first 3 seconds. All you have to do is take the change in position and divide it by the change in time. Figuring out how much something is changing just means that you have to subtract its starting value from its final value. Since, as physicists, we'll end up doing that a lot, we abbreviate that difference using the lowercase Greek letter delta. So we can use that to write the equation for average velocity. It's just delta x over delta t, the change in position over the change in time. Now what about the third scenario, when you had your foot on the gas and kept accelerating? You started out at the 4 meter mark and ended up at the 13 meter mark. So your change in position, or delta x, would be 13 minus 4, or 9 meters. You started at 0 seconds and ended at 3 seconds, meaning that your delta t was 3 seconds. Over 3 seconds, you moved 9 meters. That's 3 meters per second. The equation we use to describe average acceleration is a lot like the one for average velocity, because it's just the change in velocity divided by the change in time. So in that case, your equation would be delta V over delta T. And here's something that's incredibly handy. Since we're talking about constant acceleration, that is acceleration that takes place at a constant rate, we can rearrange this equation to get V equals V at time 0 plus AT. That's average velocity equaling to velocity at time 0 plus the product of acceleration times time. This, my fellow physicists, is an equation we'll be using a lot. We call it the definition of acceleration because that's exactly what it is. It's saying that constant acceleration is equal to the change in velocity divided by the change in time. We just use algebra to move the variables around. Now, it's worth noting that there are lots of different kinds of acceleration, ones that don't involve speeding tickets, like when something's falling. The force of gravity pulling it down is making it accelerate at 9.81 meters per second squared, which physicists often abbreviate as lowercase g. So we'll just call that constant small g. There's a capital G that's going to come up later. So the definition of acceleration is the first of the two main kinematic equations that we'll be using, but it only links velocity, acceleration, and time. What about position? There's an equation for that too, the second kinematic equation, which we'll call the displacement curve, because it takes your acceleration, your starting velocity, and how long you were moving for, and uses that information to figure out what your displacement was. And the displacement curve equation looks like this. It makes sense if you think about it. If your acceleration is the change in your velocity, and your velocity is the change in your position, then there should be some way to link all of them together. Now, there are lots of other kinematic equations too, like these, but you only really need to know the first two, the definition of acceleration and the displacement curve. The others are just different ways of rearranging these main two. And because these two equations have so many terms in common, you can use them together really easily. For example, if you know your acceleration and your starting and final velocities, you could use the definition of acceleration to figure out how much time you were traveling for. Then you could plug that value for time into the displacement curve equation and use it to find your displacement. Now that we know what the kinematic equations are, we can finally use the power of physics to find out whether you were speeding when the cops pulled you over. As with most physics problems, the first thing we need to do is write down everything we know. In this case, we know your initial velocity v0 was 0 and your time t was 7 seconds. The first thing we need to find is your acceleration, which we can get using the displacement curve. Plugging in everything we know, we find that your acceleration A was 5 meters per second squared. Then we can plug all of that into the definition of acceleration to find your final velocity, like this. We learned that you were going 35 meters per second when the cops pulled you over. That's 126 kilometers an hour, so you definitely deserve that ticket.
Ooh.
Sorry. But in this very first episode of Crash
$1
Course
million.
Physics, you learned all about position, velocity, and acceleration. We also talked about the two main kinematic equations, the definition of acceleration and the displacement curve. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel to check out amazing shows like Deep Look, The Good Stuff, and PBS Spacetime. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course.
Dr. Sheeny Samara.
She's smart.
She is. She studied in England. Somebody looked it up because they wanted to see when I first started doing. These came out. Do you guys still remember Mrs. Jenkins?
Yeah.
Her son. She had a son. Her oldest son was Nick. So we had to look that. So we started looking at the other people too. All right. Now we aren't going to go through it quite as fast or with quite as bright a smile. I'm sorry, I can't do that. But that looks like the most fun here.
Oh, yeah.
Clear the page. I have. There we go. Look, that's really. Well, it's not exactly the right size, but it's going to be enough that we can use it, I think. Ooh, that looks like so much fun.
So good to know that.
We've already done all this. Why is it just going around? I should be getting a new one. We've got plenty now. Oh. I don't All right. Let's start out with simple stuff. I would take out your,
Notebook.
yep, your formula list is what you're gonna need.
I don't have a form. Do you have a formula list?
I do.
Can I have one?
Actually, I don't. No, it's just a sheet of paper in your notebook. Yeah. Oh, you weren't here when you get to just pick a paper and you can use it on all your tests and quizzes. You will have your formulas with you.
I didn't need that.
You weren't here. So the first thing we put on it was, I don't know if this is writing the right spot. Oh, no, it's not. All right. Getting out a piece of paper. See if we can play the game. That'll work. Okay, we put down the quadratic equation, negative b plus or minus the square root, b squared minus 4ac all over 2a. We aren't going to use that for a little while, but just so,
Math, wasn't
this is a class where we just use math. All that math you learned is just so you can do
it?
science.
For two.
Okay, so now underneath that, you can write a heading of kinematics. And we're going to do some simple formulas. Just the straight, we're driving somewhere at a steady speed. From math, again, you have that, and they use, I'm just going to use a D. D is going to be used for several different things, unfortunately, but they're pretty much the same. Distance equals,
Is it meters over s squared? Oh.
equals average velocity times time. And that's what that little bar over the velocity means, or the speed. Actually, it would be speed at this point. The average speed times time. So now this, you don't have to write this down, but if you go 35 miles per hour times, make it easy, 2.0, give me another sig fig, hours, the units are going to work because I'm going to cancel out the hours and I'm just left with a distance, miles, so that would equal 70. Put my dot there, don't want to lose a significant digit, and put the unit on it. You would go 70 miles. So distance equals average velocity times time. So if we rewrite that, I would put this under kinematics too. Very simple, it's the same thing. If you solve that for average velocity equals what? You want to get it by itself in the numerator.
So V would be on the bottom right.
No, you got to have V on the top. So I'm writing it this way. You actually, the V would be on that side. You just got to get rid of the T. How are you going to get rid of the T?
Divide by T.
Divide by T. So if I divide by T on both sides,
V over T.
wow,
Or
something's wrong with the board over here. It's not letting me write straight lines, but we got that. These are equivalent equations. They're just rewritten. So since we did that, let's not stop and go in part way. What is T going to equal?
V over D. Is that right?
Not as much.
Oh, D over V.
Yes.
Because you're getting rid of V, by the way.
Over the average. Now the average velocity means that it keeps going the same all the time, or at least we're just taking it as average. We aren't going to do that very much. Most things in the world start from stop and speed up and then slow down, whatever, like dropping the sticky notes. They start from 0 and then they speed up and they eventually stop. But we could calculate how fast was it going when it hit the ground. That's not 0. When it hit the ground, it's actually moving. It eventually came to 0, but if saying that, oh, it hit the ground at 0, that would be like saying, well, yeah, if you want to drop that hammer off of a building, I'll catch it because it'll go to 0. Well, it will, but it's going to be going faster. It's going to be more dangerous. Now, that's distance, and that's going to work. You gonna give me a new one?
Come on now.
Should. It's thinking. It's thinking. Boy, is it really thinking. I'll start writing it, and then all of a sudden it'll. It's still working there. It'll go. Distance is just how far you go. For example, if let's give it. All of a sudden jump. If you're walk 3 blocks this way, and you walk 4 blocks that direction, what distance did you walk? 7 blocks. Okay, nothing difficult here. Now, in physics, usually we talk about displacement. Displacement is different because that's where you are compared to where you started. So that, here's where we ended up, this is where we started. So that would be the displacement. So distance, I'm still a little worried about why this didn't change to the new page. Distance equals 7 blocks. The displacement equals, how far are you over here from where you were here? What's the displacement? 5. Went 5 blocks. Did you do the math, or did you just know that was a 3, 4, 5 triangle? You knew that it was? Yeah. You can do the math because you know that in a right triangle, a squared plus b squared equals c squared. So 3 squared is 9.
What the?
And it lets me right there.
16.
9 plus 16 equals 25. 25 equals c squared. C equals 5. Chi Young is right. We never doubted her, but she is right. All right, so displacement is different than that. Now, if you are doing, let's say we have a horse race, and here's the infield, nice green grass in there, and we've got track going around the outside, and let's say that it is not that far. Doesn't matter. Well, let's say it's a half mile around. It's a half mile track. So our horses are running around, and here's the start. And let's say that they run around, and that's where they finish as well. So they just go around once. What distance did the horses run?
So
Yep.
they go
Half mile, okay? What's their displacement?
nothing.
0. They're still where they started. Okay, so they didn't, now they're tired, the horses are tired, but they didn't have any. Now let's say that it goes all the way around and the finish line is over here, right across from it, half of it. So the distance is,
It's a full mile, right?
is,
Full mile?
No.
you went all the way around once and then to here.
So, no.
How about
3/4 of a mile.
3/4 of a mile? You have a mile and then half of that again. Now we aren't gonna be able to tell this on here. If you were doing the displacement, they'd have to give us more, because you went from here to here, displacement would be just across here. It wouldn't even be the 1/4 of a mile, because it's where you are compared to where you were, so it's not gonna be very much at all. So if they're asking you for displacement, they wanna know where you are compared to where you were. Distance just means that, it's
How
gonna
far you
be,
traveled.
how far you traveled the normal way. And on Wednesday, I will give you some practice on this. We talking about practice.
Is it Allen Iverson, right?
Yep.
Yeah.
All right.